Good morning, more or less. So yeah, I'm James, and I work for Google in the Project Zero team. If you were actually awake at 8:15 this morning, you may have seen my boss talking about Project Zero in the sort of more abstract. But I'm one of the researchers specializing in the Windows platform, mainly local privilege escalation. This is because I have a particular thing about finding logical vulnerabilities in operating systems and platforms, and local privilege escalation is usually quite a good target for those sort of vulnerabilities. So the actual sort of description, the title is Social Engineering the Windows Kernel. But what is it I am actually going to talk about? I'm going to be talking about basically Windows access security, how it actually does it, talking about things like the security reference monitor and access tokens. And then I'm going to talk about kernel token handling and the sort of vulnerabilities you can find in that, which can lead to local privilege escalation vulnerabilities. Now, before I can sort of talk about the vulnerabilities themselves, I kind of have to frame the discussion, so I have to kind of give you a rough overview of the Windows security components involved in these sort of vulnerabilities. Now, I sort of classify it into sort of three main areas you can sort of look at. So you've obviously got the kernel itself, which contains the security components, the things which are enforcing Windows resource security. Now, each resource, then, say file or registry keys, those sort of things, have some sort of associated security descriptor with them, which contains the actual security information which says who is allowed to access what. And then finally, each process has an identity associated with it. So each process has something called an access token, which is embedded as part of the process itself. There is a reference to it from the process structure, and this is what sort of defines the identity itself of that process and is therefore how it interacts with the resource checking. So the security reference monitor is that core component of the Windows kernel which is responsible for doing security operations. So one of the big checks that is done, one of the big functions which the reference monitor exports is SeAccessCheck, and this is the thing which actually does resource access checking. You basically say, I want to access this file, and it's this function's responsibility to actually sort of look at all the parameters and decide whether, yes, you're allowed to write to that file. And SeAccessCheck is a pretty simple operation, at least if you don't take into account various other sort of extra bolt-on features which have been added over the years. Now, effectively what happens is the SeAccessCheck operation takes the current process's access token, or a access token, and the security descriptor of that resource you want to access. So this security descriptor contains things like the discretionary access control list, and this is what actually defines who is allowed to access what. And it then goes through that operation. First it checks something called the integrity level. And the integrity level is just a simple mandatory access control mechanism added in Windows Vista, which allows you to do sort of simple read-write access control. It's based on a number, so the process has an integrity level number, and the resource has an integrity level number. And if you are lower in number than the resource, then basically you're limited in what you can access in that resource. So that's the first thing which happens in this access check. It then does an owner check, and the owner check is just a simple mechanism to allow you to bypass the fact that you can actually lock yourself out of a file or lock yourself out of another secured resource. As the owner of that resource, you could modify the access control list to say, I'm not actually allowed to access my own file. That would be kind of annoying if you did that on a regular basis. So the owner check allows you to effectively circumvent that for certain limited sets of permissions. And finally, it goes into the access check itself. And this is where it looks through things like the access control list, matches your user against your groups, etc., and actually returns a success or failure to your request. If you've requested write access and you don't have write access to that resource, it's going to give you access denied and throw you out. The access token itself is actually a fairly complicated object. So it contains, obviously, your user identity. And the user identity in this case it doesn't store like a very simple number like you would typically find on a Unix system. It stores a relatively complicated security identifier, or SID, which then has a textual mapping, which you can then go back to sort of your username. But actually, under the hood, the kernel uses these SIDs all over the place. It doesn't use your name necessarily. The access token then has a list of groups. So obviously you can be in many, many different groups like you can in most other operating systems. So if you're an administrator, you're in the administrators group, and that is then used as part of the verification of whether you're allowed to access a resource or not. And then there's a few other things. You can see the mandatory label is on there, which is the integrity level. And this one in this case is medium, so this is the sort of standard level. And then finally privileges. And I don't need to talk too much about privileges, but there is a very special privilege which is part of the access token, which is done to basically give you some additional functionality later on, which I'll go into. But underneath the hood, in the kernel itself, it's just another kernel object. It's just another allocated structure with some sort of data inside it. And just like any other kernel object, you can reference it and get access to it from user mode. But of course, it wouldn't be just a simple case to have one single type of access token, because that would be obviously simple. We don't want just one, we need multiple. So in this case, there's multiple sort of categories of access token. You have your normal token, which is going to be used in 99% of operations. If you look at UAC, if you're a split token admin, so on UAC where you just see the prompt and say, do you want to click yes or no, that's called it's a linked token, and it's sort of bound to your existing token and technically sort of sits apart. And then there's two operations you can do on a normal token. You can filter it, or you can create what is called a low box token. And low box tokens are used for Windows 8 Metro applications. And filter tokens are called restricted tokens usually, and they allow you to apply special filtering operations, remove groups, remove privileges, that sort of thing. So you can find all these different tokens in actual normal operation. But there's loads of interesting fields, which will come to a few of them as we go along. So things like the token ID and the parent token ID, obviously your groups and your privileges, etc. Now, when you actually access this from user mode, like all kernel resources, you need a handle. You can't just say, I want to open access token at this kernel address, because that would obviously be a massive security flaw. So instead, the kernel hands you back an opaque handle, which you can then use to reference it using the various system calls. And there's some very important rights you can get, some privileges you can get on that handle, which affect how you can interact with that token itself. So things like duplicate. So one of the functions you can do is you can duplicate a token and create a new token from it. And you need a specific right on that handle to actually do that. Another things like assign primary is when you're trying to create a new process, or impersonate, which is about impersonation, which I'll obviously also go into. But it wouldn't just stop if you had 4 types of access token. Of course, there's actually 2 types of access token relative to the 4 types of access token you already had. So now we've got 8 types of access token, potentially. The first one is probably one of the most important, and that's the primary token. And the primary token is used for the process security. So every process has an assigned primary token with it. The other one is an impersonation token. An impersonation allows a service to pretend to be someone else. So whenever you're doing an access check, if you can impersonate another token, you can basically pretend to be that person. If you try and access those files, it will succeed. But these are sort of two, while they're technically the same, they're subtly different. They just have this difference in whether they're a primary or an impersonation token. But of course, there's more, because not only do identification tokens subtly differ from primary tokens, you can also have 4 different types of impersonation token, because for security reasons, you kind of want to have some sort of differentiation. And in this case, the differentiation is here for security reasons. So the top 2 on the right-hand side, delegation and impersonation, if you are assigned a token with these levels, you can pretend to be that person. You can access their files. You can access their other secured resources. From the kernel's perspective, you are that person. However, the bottom 2 do not give you that power. Instead, identification just basically allows you to say that this person is Bob Smith, and I trust him as far as that, but I won't actually allow him to directly open a file. You would still need to be able to open the file indirectly, and you can just use this as a marker to say, I want to open this file. And finally, anonymous is the, technically it's not anonymous. It is still the same access token, but it says it's an anonymous token. That interplays with impersonation, but in general, we don't have to worry about that too much. Now, when it comes to duplication, there's an important security requirement here, namely that if you have a primary token, it should be possible to convert that into an impersonation token. And you can just call the duplicate token function, and you effectively convert between one and the other. But if you just get an identification token, if you've just got a token which says this is just saying who this person is, not actually who, like, you're not actually that person because you couldn't access their resource, well, you're not allowed to go back. So unless you've got a full impersonation token, you're not allowed to convert that back to a primary token. Otherwise, you could potentially create a process under another user account and do some damage. So this is an important security restriction. Now, another thing they do when you duplicate is they assign a new identifier for that token. So every token in the system has a unique identifier. It isn't some like clever trick to generate this number. It is just a single incrementing counter in the kernel, which just for every token it gets incremented. And this counter is used for a number of different things, as we'll see. Now, once if you've got a handle to an impersonation token, you actually need to apply it. And the way you apply it is you set the current thread. So obviously in Windows, processes and threads are sort of distinct entities. They're both, threads are the scheduling element, and processes are just sort of containers for the sort of memory layout of that operation. So when you impersonate, you're actually impersonating at the thread level. You're not impersonating the process. The process still has its primary token, but you actually change the individual thread. So there's a few different ways of getting that thread token set. One of them is direct setting. You can just call a function which says, hey, I've got this handle to a token. It's got impersonate privilege. Can you assign that to my thread? And it can go yes or no. There's then the indirect setting. So indirect setting is where you have a scenario such as named pipes. And named pipes have a special feature which allows you to impersonate the client end of a named pipe. And there is a special function for that. And you never actually get a direct handle to that access token. It's all sort of managed for you under the hood. You never see it. Finally, obviously, you've got the kernel can itself set impersonation tokens using various different APIs, say PS impersonate client. Now, there is a very important security problem with impersonation, and this problem manifests prior to Windows 2000. So obviously, it's a good 15 plus years ago when this was a major issue, but you have a problem in that if you have a normal user and it could arbitrarily impersonate an access token, well, if you have, say, named pipes going around, if you tricked an administrator to open your named pipe, you could impersonate that administrator as with full impersonation level, and you've just gained admin privileges. So we don't want that to happen. So obviously, we need to sort of mitigate that risk. And the way it's mitigated is by adding a privilege to the operating system, the impersonate privilege. And this is something which ends up in your primary token in your process and says, this process can impersonate any other user. And obviously, this privilege is quite important and quite bad for security if it's misused. So only administrators and service accounts will typically get this privilege. But of course, if it doesn't exist, there has to be some operation to kind of allow you to do impersonation in some way. So what happens is it follows this process. It basically says, if that process has impersonate privileges, then you can set that thread, that's fine. You can set that token. Otherwise, like we do an integrity level check, because obviously you don't want, say, a low integrity process impersonating a high integrity process, because then you potentially got security risks for that. So again, it does a check. And it basically then sort of says, is the user the same as the impersonating user? If it is, let it through. If all those fail, what it doesn't just say, well, I'm sorry, you're not allowed to impersonate that user. Because there is actually some sort of useful benefit to being able to get impersonation, at least for identification purposes. So what the kernel does is it says, all right, you can't impersonate them at a level which you could actually interact with the operating system, But tell you what, I'll give you an identification token instead. I'll reduce the level, the security level, and I'll assign you an identification token instead of the full impersonation token. So what can you actually do if you've ended up with this identification token? Well, it is almost, from a kernel perspective, exactly the same as a full impersonation token or a primary token. The only difference is like there's one D word pretty much in the token which is different between one type of impersonation token and another. So there's various functions which take identification tokens, usually from user mode, and allows you to interact with them as if you were doing an access request. So the NtAccessCheck system call will happily do an access check against an identification token. Because from the kernel's perspective, it's all the same, arguably. It all has the same groups, it has the same privileges, so it can still do it. But in the kernel space, anything which does access checking should always call SeAccessCheck, because that's the only one which actually does verify that the caller has the privileges to actually access that resource. But what this leads me to is the whole title of the talk. The fact that identification tokens effectively will just kind of will be handed out to you in most situations. If you fail to impersonate that token, it will still hand you back an identification token. So I consider these to be sort of almost like fake IDs. You are effectively pretending to be someone. You're not. If someone actually checks hard and calls a proper access check, it's obviously going to fail. It's going to go, no, sorry, you're not actually that person. But if you find the security guards like having a bad day, you can't really be bothered to check, like, well, maybe he'll let you through. Like, it looks like a real ID, as far as you can tell. Here, have some alcohol. You're obviously 21. So that's the sort of setup to the whole sort of concept of this social engineering in the kernel, because you want to find bugs where, yes, that security guard is having a bad day. He's not fully checking. But before we can actually exploit a bug like that, you need to actually get hold of one of these identification tokens. If you haven't got one of these tokens, well, you're not going to do anything. But you also need to kind of get one which meets some specific criteria, whether that be you need an administrator token, you need a token for a particular user. Without being able to do that, you obviously are a bit stuck. Fortunately, there's a multitude of ways you can get access to tokens, and this is just some of the few. So obviously the first one, if you know their password, you can just log them on. Now, of course, if you know their password, then that's probably game over anyway. But of course, if you know their password through some other means, or you can brute force their password, potentially you can just log them on. And what that function returns, is an access token, generally a primary token as well. So it'll give you basically full access to that token. Now, of course, you can't necessarily impersonate that as a normal user if you're trying to impersonate a different user, but it's still a potential interesting attack vector. If you're running as a split token admin and you need an administrator token, there's a system call for that. Just give me the linked token, which is associated with my current token, and it will return you back what is effectively an administrator token. Now, it's not stupid enough to give you back a full impersonation token, it's only identification, but it's a really quick and easy way of getting an administrator token as a normal user, assuming you're actually running as a split token admin. A classic trick, and this has been known pretty much forever in sort of NT security, is that things like named pipes will give you back a token. So if you can convince, say, a local system service to open your named pipe endpoint, which is not that hard, even though you can't fully impersonate the local system, you will get back an identification token for it. And so you can kind of pretend to be local system. Similar thing with RPC and DCOM. You can do a very similar thing. It has the same sort of technology. And there's also things like NTLM Negotiation. If you can get a way of a local system process to negotiate NTLM to you, so the NTLM challenge, you can actually parlay that into a full token. And this is a full impersonation token. Again, you couldn't assign it because it will just reduce it to identification level, but you can still get this full token. And you can use things like WebDAV, and there's public documentation how you would actually use that. One final interesting one I found. So logon user is the sort of traditional way you log on a user onto a system. But there's also a second function called LSA logon user, LSA being the local security system of Windows. And this has a special mode designed specifically for Kerberos called Services for User. And it turns out, at least on Windows 8.1, as a normal user, I can call this API, give it any local user or any Kerberos or any domain user who's allowed to log into my current machine, and it will return me an identification token for that user. So if a local administrator, just say, I want the administrator token, here, have an administrator identification token, so on and so forth. And yes, it works with domains as well. But you do not have to provide a password. So this is distinct from logon user, where you need the password of that user. You can just say, give me that, and it will return you that token. So I'll just show you a quick little demo of a tool I wrote to show you sort of capturing different access tokens. If I can actually find my, okay. That seems to be dead. Yes. Having seemingly problems with equipment today. Okay, to save some time, I'll leave that to run, and I'll demo that a bit later when I've got some other demos I can run, so we just leave that to boot up. Okay, so we've now managed to get our identification token. We can use this to try and gain extra privileges, find ways in the security system where they're a bit weaker in checking the security of your token, and therefore use it sort of as a fake ID. So each of these are sort of like, I'm going to discuss the sort of actual vulnerable pattern. So you can actually look at these from, say, static analysis perspective. You can say, okay, this piece of kernel code there's a good chance it's vulnerable to this sort of attack. And then you obviously can take this sort of impersonation stuff and you can actually sort of play with that. So first, we need to know how the kernel interacts with tokens themselves. And there's, as you can see, quite a few different ways that access tokens can manifest in kernel code. And you've got the sort of public API one, so things like the process and thread manager has functions to reference the primary token. It has functions to reference the impersonation token, and so on. You've then got system calls, and technically kernel code doesn't need to call system calls for this, but sometimes it will. And there's functions to create tokens and build filter tokens and open the current process token. And in this case, it will return you a handle back instead of a pointer to an object, but it is still technically opening a token. And sometimes you'll see it open the token using, say, open process token, and then call object reference by handle, which then returns the pointer to the token when it could have just called PS reference primary token, but that's, of course, beside the point. Then you've got things like direct access. This is reserved primarily to the kernel itself, or the latest Win32k elevation of privilege, which is modifying the current process's token. But normal operation, you shouldn't see third-party drivers munging in the eProcess or eThread structures. But theoretically, they could. And the final one, which you'll see somewhat, is the I/O manager. Whenever you create a file in the I/O manager, the driver gets a I/O request packet, and as part of this I/O request packet data, it actually has like an access security context, which indicates who opened it and the access token it captured. So the first really obvious bug, which I've described the sort of primary tokens, impersonation tokens, all that sort of stuff. The obvious bug is, if I try to do a security check manually, and I get hold of an access token, and I don't generally care too much that it's an impersonation or a primary token, because I just want the current sort of security context in which I'm running. If we don't check the impersonation level is impersonation level or above, well, that's a bug generally, because what that means is that code is going to sort of operate under the assumption that the person calling it is that person and is that actual impersonation level. But of course, if it does some sort of security critical operation at that point, you've then got yourself potentially an elevation of privilege vulnerability. So there's a few different variants of this. You can do it manually. So the previous one is capture subject context, and this effectively captures a structure which has the primary token any impersonation token, the impersonation level in it. Or you can do it manually if you like. There's also an internal Windows kernel one called reference effective token, which kind of does the same as capture security context, but only returns you one token. So it's kind of interesting. Now, I can give you a real-world example of this one. So this was a bug I found in the application helper cache control, which is used for sort of application compatibility shims. And it's basically a mechanism through which you can do sort of application compatibility and apply fixes for processes which don't work quite right on the current version of Windows. And it was doing an admin check. It's saying, is the current caller an administrator or not? And the only thing it was doing was basically querying for the token's user SID and comparing it against local system. So if you have any token, any identification token, which claims to be local system, well, you can bypass that check pretty easily. There's also a secondary check in there, which is kind of interesting because of a difference in operating system. But this one only specifically affected Windows 8.1 in terms of actual exploitation, although I believe it was fixed in 7 as well. So hopefully if my VM is actually booted, God damn it. Let's try that again, shall we? Well, yeah, when I came up here, my machine just killed itself, like completely. So I had the VM up all and running, and I had everything else up and running, and it decided that, no, it was going to kill itself. And I don't like it saying preparing Windows. That sounds a bit ominous, really. What? Wow. I think something's completely nuked it. Oh. Yeah, somehow it completely nuked itself. I think I blame the Mac, to be honest. I'm sure it's the Mac's fault. I apologize for this. I should have done that before, really, shouldn't I? Always come prepared with a snapshot which is currently running. Right. So, first thing, I can give you a quick demo of the tool I've written. I hope to release this sometime after the conference. Unfortunately, I couldn't sort of fit it in to get it released because you have to go through various procedures at Google to get it released. But this allows you to sort of look at different things. So obviously, you can look at a process token itself. And so it gives you like a rundown of all the different things. I've highlighted, obviously, the token type of primary and impersonation level of none, because a primary token has no impersonation level. And there's various different things in here, like groups and stuff. So, for example, I can do the services for users. So I've obviously, my demo actually had like administrator set up, but I don't actually have that on here now because it's killed itself. But I can just call create. And without passing a password for my current user, it's fashioned me a brand new token. And this will work, as I say, for administrators as well. That's not a problem. And there's some service stuff. So the way I exploited this application cache one is you can create you can get an impersonation token off a system service running DCOM. So I can just click that, and it returns you local system. Oops. Go away. So yeah, so it's NT system. But obviously, if you look down, it is obviously an identification token. It's not actually a impersonation token. But that's good enough for exploiting that vulnerability. So if we actually try and run this. So this is all available on the issue tracker, the Project Zero issue tracker. I just run that, and it doesn't work. Awesome. Oh, I know why. try that again. Okay, so that's elevated that, and hopefully, if I can bring up Process Explorer, we'll see that we've obviously got calculator running as it's running as calc, and we can't access it because it's actually running as an administrator user. So from a normal user, we've pretended to be local system, and then obviously managed to use that vulnerability to, using the other functionality to elevate ourselves to an actual administrator user. Okay. So I pointed out there was another function call there, and this is SE token is admin. So is that also bad? Well, it turns out on 7, yes. In 7, SE token is admin just checks whether that token has an administrator group. It never checks that it's actually a valid impersonation token. In 8.1, however, that check has actually been added, which is kind of an interesting security advancement. This actually seems to be related to low box tokens and the modifications done to the kernel for that. But yeah, on 8, that function would have failed, but on 7, it would have succeeded. So the next bug is crafted subject context. So the subject context itself is a public structure. It's in the Windows driver kit development headers. And if you actually look at it, it has a primary token field, and it has a client token field, which is your impersonation token. But because it's a public structure, and things like SeAccessCheck require this subject context, well, there's kind of an incentive, you know what, let's just fake one out. I've been passed an access token pointer. If I just set the primary token as that access token, that'll be fine. I can do my SeAccessCheck, everything works. So we do something like that. But unfortunately, there's a problem, because SeAccessCheck only checks the impersonation level of the token as long as the client token field is set. If you set an impersonation token to the primary token, well, it thinks it's a primary token. It never actually checks that it's a primary token. It never actually checks that it's a correct impersonation level token. So by doing this, you've potentially opened a hole for yourself. Now, this is a real-world example in Windows 8.1, but as far as I can tell, it has no significant security impact. But it is actually a bypass. Effectively, it's checking whether you're allowed to read an atom or delete an atom, which is a special structure in Win32. And it references the effective token, but never actually checks that the impersonation level is a certain value. It then just assigns that value to the primary token of a crafted subject context and calls SeAccessCheck effectively. And so this sort of call might just be because that's actually the operation in which they want to occur. They want to check whether that user would be allowed to use it irrespective of whether you're really impersonating. But it's hard to tell because there doesn't seem to be an obvious security risk with it. But you can find it in other places. Another thing is system thread impersonation. So the kernel calls for impersonating a user just take an access token of some form, a pointer to it, and the thread in which you want to impersonate, and then the level you want to set it to. So this is regardless of the actual token's level itself. Now, if you end up with impersonating in a process which has the impersonation permissions, but takes your token from somewhere else, well, it potentially can just assign that impersonation token to something. And that thread again gets elevated. So where it thought it was trying to impersonate you, it may have actually tried to impersonate local system and done something more dangerous. One more bug is leaky tokens. So when you do things like named pipes and you try and do the impersonation there, you don't ever get direct access to the token. So even though the sort of token stored is actually a full impersonation token, you're never allowed to access it. And it turns out that some code makes the assumption that, well, I could just, if I get a kernel object, I'm pointed to it, if someone asks, I'll hand you back a handle to it, because why not? And this is usually obviously in drivers rather than the kernel itself. So it may allow you to access a token you would not normally be allowed to access at impersonation level. So a real-world example of that was in Win32K. And Windows 8.1, I believe, introduced a new system call, NtUserGetClipboardToken, which returns you a handle to the token which last wrote to the clipboard. And this could be either the impersonation token order primary token, and actually gave you a reference directly to that object, not just a copy of it, not a clone of it, or anything like that, would actually return you back an actual instance of that. And that has actual implications, because as a lower level user on the same desktop, which you need to do to access the Win32k, I can usually get sort of read access to any token which happens to be interacting with that desktop. But read access has token duplicate access. So one thing I can do, I can duplicate the token to create a new impersonation token, and then I can lower the IL level. And that effectively allows me to bypass the majority of our impersonation check. So if you think about it in the UAC example, the UAC admin is running as an administrator, but it's still running as you. And the only thing which stops you impersonating that token, if you ever got hold of it, was the integrity level. It runs at high, and I run a normal user as medium, so I can't impersonate. But of course, if I can get access to the raw token, I can lower the level and actually manipulate it that way. So I can just quickly demo this, assuming everything hasn't died. So if I kill all that. So this program is basically sitting there in a loop, calling this function, waiting for an administrator to write to the clipboard. So obviously I've got to simulate that. So I'll bring up Notepad. Close him. And then what it will do is it can basically impersonate that administrator, and for all intents and purposes, the kernel now thinks it's an administrator, just running as medium integrity instead of high integrity. But that doesn't really matter, so we can then write something to the Windows folder, I believe. So if we copy and paste from him, okay, so he's gone away. If we go to, I believe, Windows folder, we should find test.txt, which has been now written by our higher privilege process, even though we never actually had access to that. So obviously that's more of a UAC bypass, but there is other sort of interesting aspects you can do with that. Now this one is also an interesting one. It's similar to that sort of impersonation bug. So basically, if you have the kernel can do duplication calls arbitrarily and can say, I want actually this kernel to be, this token to be a primary token. And if it doesn't actually correctly check, well, then potentially you've got, again, a security issue, because one token which is not valid for use can suddenly become another token which is valid in the use case in which you're trying to set it. So in this case, a real example was this one. So when you create a new process, you have a mechanism to assign a primary token to it. Now again, that would be a risky maneuver to just allow anybody to do that. But one of the things which kind of is supposed to prevent this is it's hard to get a primary token if you do not have a full impersonation token. So it's supposed to require a primary token to be assigned to the process. And all you need, as it says there, is token query, token duplicate, and token assign primary access rights. But if you actually dig into the code, so CreateUserProcess is implemented by a system called NtCreateUserProcess. It first tries to reference this token for new process. So you pass it as a handle, because this is coming from user mode. So you pass it a handle. And actually, all it really requires is token assign primary. It turns out every impersonation token will give you this right back. If you create a duplicate of a handle, of a token, it will just allow you to assign primary rights to this handle, even though it may not actually be a primary token which could be assigned to anything, theoretically. So you then dig a bit further. So obviously we've passed this check because we can pass an impersonation token at an identification level as long as we have this assign primary right, which we can get very, very easily. But then if you actually look at when it actually creates the token, it calls this internal sep duplicate token function. And this function does the duplication, but does none of that verification check, which the normal operations would do. So you do not get the verification that an identification token is being converted to a primary token. And so effectively, this circumvents the security of it and allows you to assign arbitrary impersonation tokens as the primary token of a new process. Now, in and of itself, that probably shouldn't be a major problem, because like the impersonate privilege, you actually have a sort of corresponding assign primary token privilege. And only things like system services, like IIS, have a privilege to do this. So one of the things you could do with this vulnerability, you could easily elevate to local system using this by capturing a local system identification token and then creating a new process as local system. But that isn't that useful. Hopefully you have an implicit problem if you've got code running in service accounts. So I thought, is there another way of abusing this? And the verification, like the impersonation check, does some sort of determination as to whether that token is appropriate for actual use in this scenario. So that a normal user can create some processes with different user tokens, just not all processes. And there's actually two checks. The first check says, is this token a child of your current token, your current process token, effectively sort of a parent-child relationship. And this is sort of the case of create restricted tokens or filtered tokens. Filtered tokens always assign the parent token ID to be the token ID of the original token. The second one is it a sibling token? Is it the same parent token ID and the same authentication ID? And authentication ID is effectively the logon session unique identifier. And this is the case of duplicate token, but also interestingly, create lowbox token. Now, create lowbox token is also used not just in metro applications, it's also used in things like IE's enhanced protected mode. So potentially, there's a way of getting out of IE's enhanced protected mode down to just normal protected mode, which technically isn't the security boundary, therefore you've effectively sandbox escaped out of IE. So I can quickly demo that. Oops. So if I load up IE, so just check I'm running enhanced protected mode, should be doing. Check from here. Yeah, so as you can see here, we've got IE's running according to Process Explorer as app container. So this is running inside the restricted enhanced protected mode sandbox, which for the most part is considered to be a security boundary. So that's 3096. So if I do, so all I've got here is a simple tool to inject a DLL into the enhanced protected mode process, just to demonstrate, effectively, if you had an RCE, we can demonstrate that it actually would inject into that process effectively. And what we'll do is we'll try and create calc and try and break out of the enhanced protected mode sandbox. So we've now got a calc, and obviously we now see calc is actually running as low instead of app container. So effectively we've now broken out of the app container sandbox using that. So even though we never had assigned primary token privilege, there was still some security impact with this vulnerability. So just a few more bugs as I go towards the end. Time of check and time of use bugs. Whenever you open a resource, such as a file, it will usually it will check you when you try and open the file. But of course, there's a potential operation that you can switch the token between the open call and some other operation. So a classic one is like device I/O controls. So device I/O control is a sort of, once you've opened a file, you can send it arbitrary control codes. And if the driver assumes that because local system must have opened this file, that local system is still running and has opened this file, you can kind of get a time of check, time of use. You can open as a normal user and then send it a control code impersonating another user. So again, obviously, I want to provide real examples for this. This one was a bug in the WebDAV driver support, and it was part of a device I/O control, and all it did was it checked whether the current authentication session was the local system's authentication session. But it never made a check, obviously, for the impersonation level, because probably there was some tacit assumption that kind of you may have already been opened at local systems. You couldn't have been impersonating at a level you wouldn't be allowed to open that file. I think the final one on this is vulnerable system calls. So I showed that there was some system calls you can call to make access to these tokens. There was an earlier version of this. When you actually see them now, the only documented ones are the EX variant, so SE Open Thread Token EX. And there was basically a sort of a bug in these system calls from a kernel caller perspective. Basically, the kernel tries to separate handle tables. So any file you try and open in kernel mode should have a kernel-only handle. But you have to pass a specific flag to say, I want to only open a kernel handle. Because if you don't specify that flag, that handle gets opened in the current process, and that current process can then manipulate that token. And these calls actually have no way of specifying, I want to open a kernel handle. So basically, there's no way, you should not use them. If you see a driver using these functions, there's maybe a security vulnerability there. So the final little bit of this presentation is a few bits of changes that have been made in Windows 10 specifically, but also in Windows 7 to handling of tokens. The first one is SE token is admin is fixed. Awesome. So they've now actually backported the impersonation level check to SE token is admin. I didn't get acknowledged for that. I don't know whether NVIDIA had something to do with this, because NVIDIA had a similar bug using this same function, and obviously they did say they would talk to Microsoft about it, so maybe that's why it got fixed. And Windows 10 itself, this is a slightly older build than is currently available. It also has modified the impersonation level check to add some new weird capability checks and elevation checks. First one is it's added a new group. So if you've got this group in your normal group list, you can impersonate more types of tokens than just the sort of restricted, it has to be you or it has to be a certain sort of class of you, which is kind of interesting. If you can find a scenario where this is used, it may be a particularly interesting vulnerability. The other one would actually combat my bug I demonstrated with the clipboard token, in that there's now a check for, is the current token elevated, and therefore, if the process token isn't elevated as well, you're not allowed to impersonate. But interestingly, this is actually behind a compatibility flag. So currently, in the current build of Windows 10, this does not get enabled, but it is there and can be enabled. So that's the end of my presentation. I know there's quite a lot of stuff in there. It's worth looking on our issue tracker, which Chris showed earlier today. You can just look for my bugs on there and have a look at some of the other token bugs I've actually done. But if anyone has any questions about this, obviously ask away, or wait until, if everyone wants to get to lunch, you can sort of bug me over lunch and ask about that sort of stuff. So thanks very much, and anyone got any questions?